Okay, so what we're going to talk about now are oscillations. And oscillations are really important to physics. At a fundamental level, all the particles that we're made up of can be described as oscillations of quantum fields. So really at a fundamental level, that's what we're made up of. We're made of oscillations. But oscillations occur at all scales in physics, from the simple mass on the end of a spring that oscillates up and down, to the orbit of the sun around the center of the galaxy that is something that takes 200 million years or more to actually make a complete revolution. So what we've got here are some little fun demos showing you oscillations. So a simple example of an oscillation here, we've got a superconductor that is quantum locked, to a magnetic field, and will oscillate backwards and forwards on a curved track. So that's one example of an oscillator. A more common example, and one that we'll deal with a lot more in this course because it's a lot simpler to describe mathematically, is the mass on the end of a spring. And so if I take this mass and I start it oscillating, you can see that it undergoes a repetitive motion. Just like our little oscillator here, it went backwards and forwards. Here we've got the mass on the end of the spring moving up and down. So in physics, we want to be able to quantify and describe such motion. So if we look at this motion here, what we can do is we can measure the time it takes for the mass to undergo one complete oscillation. So if we time it from the bottom of the oscillation here to the top and back down to the bottom again, that time is called a period. And the slower the oscillation, the longer the period of the motion. Now, if I take it from somewhere else, for example, this midway point, then you have to time it from when it gets to this point with the same velocity. So it's the time when it leaves this point to when it returns having the same velocity, because obviously in the midpoint here, I can go up and I come back down again, and that would only be half an oscillation. So that's a period of an oscillation. Now, what's also useful to describe is the frequency of oscillation. The frequency is the number of oscillations per second if we're using SI units. And so the units would be per second, but we don't use those. What we use in the SI system is the unit called the hertz with the abbreviation HZ. And so the higher the frequency of the oscillation, the more oscillations per second that our system will complete. Now, the other characteristic of the oscillation is going to be what we call the amplitude. So the amplitude is the maximum displacement from the equilibrium position. So here is the equilibrium position of this mass, and if I pull it down a long way, then I'm ending up with a large amplitude motion, right? So the maximum displacement from this equilibrium position is what we call the amplitude. However, if I only pull it a small distance from this equilibrium position here, then we end up with a small amplitude motion, right? So the maximum displacement from equilibrium is the amplitude. Now, for most mechanical systems that we'll be dealing with here, the amplitude is measured in units of distance. So the amplitude for this mass spring system is going to be the distance from the equilibrium, and so that has units of meters. Similarly, for this quantum locked oscillator we had here, this is a displacement in terms of meters because it's a physical distance away from the equilibrium position in the center. However, if we look at this oscillator here, which is a pendulum, then we measure the displacement as an angle from equilibrium, and so therefore the units of this amplitude actually depend on the system we're looking at. Here, in the pendulum's case, the amplitude is measured in radians, which is a dimensionless number. Here, it's measured in physical distance, which has units of SI units of meters. So now what we're going to do is we're going to dive in and apply Newton's second law to the motion of these oscillators to understand how they oscillate and how the period and the frequency and the amplitude are related to one another. Here we have a mass m that is attached to a spring that obeys Hooke's law, so that the force that the spring exerts on the mass is proportional to the displacement of the mass from the equilibrium position. And this is the equilibrium position here. And note that there is no friction on the surface here, so that the only force that acts on this mass is due to the spring. And we're also going to assume that if we go to a negative x out here, that we have a force acting in the opposite direction that will be equal to k times x here. So let's call that x prime. And if we go to a negative x prime, then we'll have a force that's acting in the other direction, so moving it always back to this equilibrium position. So in other words, this spring obeys Hooke's law both in extension and in compression. Now we want to know what this displacement is, and since this is an oscillating system, this displacement is not a constant value. We aren't just going to come up with a simple numerical answer, we're going to come up with a function of time. So in other words, x here is going to be a function of time. So what we want to do to find x is write down Newton's second law for this system. So Newton's second law is force is equal to mass times acceleration, and so here our force is going to be minus k times x, and this minus comes about here because we have the force is acting in the opposite direction to the displacement. If the displacement is positive in this direction, then we have a negative force along here. So this gives us our minus sign here, and this is equal to mass times acceleration. Now we can write the acceleration as a differential, so we can write this as mass times d2x by dt squared, and this is using Leibniz, and this is the notation that Leibniz used when he came up with calculus. Another way of using it, which we'll use here because Newton actually invented it for the mechanics that we're doing here, is to use the dot notation. And so since it's a second order differential, we have two dots. A dot above a figure means differential with respect to time, and it only means with respect to time. So this is why we actually use Leibniz's notation, because it tells us specifically what we're differentiating with respect to. But when we're doing mechanics, we often have a lot of these differentials with respect to time, and so to save time you can write it with a dot. A single dot means one differential with respect to time, two dots means the second order differential with respect to time. So let's rearrange that, and we have x double dot is equal to minus k over m times x. And so if I write this in Leibniz notation again, just to confirm that we understand both ways of writing things, then this is equal to d2x by dt squared. So what this is telling us is that this function of x, which is a function of time, when we differentiate it twice, we get a constant times the same function. So what we're looking for is a function that when we differentiate it gives us the same result. So let's try see if we can guess. We know a function that when we differentiate it gives us the same function, and there's only one that does that, so let's use this, and that's the exponential function. So ae to the omega t. So this is the Greek letter omega, it's not a w. And then if we differentiate this with respect to time, then we're going to get omega times ae to the omega t, and then when we differentiate it a second time we get omega squared ae to the omega t, and that is just omega squared times x. So that looks promising. We've got the second order differential with respect to time, x double dot, is equal to a constant omega squared times x. But we've got a bit of a problem here. K is the spring constant, and this is positive, and m is a mass, so that's positive, and so therefore k divided by m is going to be positive. And then you put a minus sign in front of it, and what you've got is you've got a negative number multiplied by x. Now let's look at our test function that we were guessing. Here we have omega squared times x. So what we need is, this tells us that we need omega squared to be less than 0. Now that is only one way we can get that, and that is we need an imaginary number. And so this is where imaginary numbers are going to come in. So let's go back to our function here and let's try something a little different. So let's try x of t here, and now we're going to say let's use z here. So this is a complex constant now, so it's got a real and imaginary part, and we're going to say e to the I omega t. Right, so I here is, this is defined so that I squared is equal to minus 1. So we differentiate this, and what do we get? We get I times omega z e to the I omega t. We differentiate it a second time, and now we're going to get I squared. Well, I squared is minus 1, so we get minus omega squared z e to the I omega t, and that is equal to minus omega squared times x. And we now have a function that works as the solution to our equation that we got from Newton's second law, right? So this is actually called the equation of motion, and we have a solution to it that x of t is equal to z e to the I omega t, where omega is equal to the square root of k over m, because omega squared is equal to k over m. So we've got a solution. So is that the only solution that we have? Well, no, it isn't, because what happens if we try this solution here? So we're going to say x of t is equal to, and now I'll use another complex constant, we'll call that y, and we'll say e to the minus I omega t. Now x dot is going to be equal to minus I omega times y e to the minus I omega t, and then x double dot is equal to minus omega squared times y e to the minus I omega t, and that is equal to minus omega squared times x. So this is a different function. It's not the same function because we've got minus I omega t here instead of plus I omega t. So we can't get to this function just by changing the value of z from this function. That isn't going to work because we've got the minus sign that goes here. So this is a different function which is also a solution. So the question is now, which of these two solutions is the right one? Right? If we've got two possible solutions, which one do we want to use? So let's have a look at that. Okay, so we've managed to come up with two solutions to our equation that x double dot is equal to minus omega squared times x, where omega squared here was, or omega was equal to the square root of k over m from our original system. So the nice thing with this is it's what's called a linear differential equation, in which means that the differential terms are not squared. We don't have x double dot squared or x double dot cubed or x squared here. It's all linear in terms of the differentials and the function itself. So what that means is let's define a function h of t, and that's going to be equal to f of t plus g of t, where these are both solutions to the equation where we have, so this is both solutions to the equation. So what this means is that f double dot is equal to minus omega f, and g double dot, oops, is equal to minus, sorry, that should be omega squared there, minus omega squared times g. So these are both solutions to our equation. So what we're wanting to know is this a solution? Right? Is this h of t, if we add these two things together, a solution? So let's see if that is the case. So h double dot is equal to d2 by dt squared of, and then h is equal to f plus g, and this is clearly, since we're adding these two things together here, the differential acts on each of these two things separately, and so this is going to be equal to f double dot plus g double dot, right, where again this means d2f by dt squared, d2g by dt squared. So since these are solutions to our equation, we can rewrite these two terms here, and we can say that these is equal to, here is minus omega squared times f minus omega squared times g, and then I can just factor these together, so I get minus omega squared times f plus g, which is equal to minus omega squared times h. So what I've just shown here is that for this linear differential equation, if I have two solutions, f and g, then the sum of those two solutions is also a solution to the equation. So what does that mean? It means that we can now write x of t as the sum of those two earlier solutions, so z e to the I omega t plus y e to the minus I omega t, where these were both complex constants. And this is what we would expect, because what we've got here is a second order differential equation. So when we solve it, we're implicitly integrating twice to get rid of this differential. And each time I do an indefinite integral, I end up with a constant. And so since I've done two indefinite integrals, I've got 1, 2 constants. So this is exactly what you'd expect, and if you solve an nth order differential equation and you don't have n constants, that means you're missing a potential solution. So I've got my overall solution by adding these two separate solutions together. So is that it? Are we done? Well, this is where we run into a problem. The mathematician is now done, but the physicist is not, because this equation here, x is a displacement. And if you look at your ruler, you will not notice that it can measure imaginary displacements. The only numbers on there are all real numbers, and that means that x must be real if this solution is going to represent a physical displacement. However, we've got these complex constants, we've got a complex imaginary number up here, and so we have a problem. This is not in general going to give us a real number. So we have to do something to it to ensure that we get a real number. Now, there are going to be solutions which aren't real, but those are not physically interesting for this particular case. So in other words, we've got an equation that we can solve to find out where the object is, but not all of the solutions are going to correspond to physical solutions of the system that we're considering. So how do we get rid of the complex, the imaginary part of a number? Well, if you remember back to our section on complex numbers, if you add a complex number to its complex conjugate, then you have x plus iy plus x minus iy, oops, that's a y there, and that is equal to 2x, which is real. So what we want is we want this number here to be the complex conjugate of this number here. So first thing is that we also need to remember one other relationship, which is if I take the complex conjugate of a multiple of two complex numbers, then this is equal to the complex conjugate of the first number multiplied by the complex conjugate of the second number. So if I look at these, I've got a complex number here multiplied by a complex number. I've got a complex number here multiplied by a complex number. So what that tells me is that I want z to be equal to the complex conjugate of y, and I want e to the I omega t to be equal to the complex conjugate of e to the minus I omega t. Right? And if these two things are not true, then I'm not going to then I'm going to get a complex number out of here. So I require these to be the case if I want a real number, because then that would make this term the complex conjugate of this term, and then the imaginary parts cancel out. Okay, so how do I go about that? Well, let's try this first, because I don't really have any control over these two terms. So if I write e to the I omega t, that is equal to cosine omega t plus I sine omega t. And e to the minus I omega t is equal to cosine minus omega t plus I sine minus omega t. Well, this is nice because cosine is an even function, which means the cosine of minus x is just equal to the cosine of x. So I can write this just this cosine of minus omega t as the cosine of omega t, because they're equal. Sine is an odd function, so the sine of minus x is equal to minus the sine of x. So I've got a minus sign now, I, and then sine omega t. So if I look at these two numbers here, the real part is the same, the imaginary part is flipped, and so this is true, right? This relationship here is correct. E to the I omega t is the complex conjugate of e to the minus I omega t. Okay, so that one's correct. So how do we make this correct? Well, here I've got more control because I can pick these constants. Now, for any complex number, I can write a complex number here as b e to the I phi. And b here is real, and it's the modulus. And phi here is real, and it's equal to the argument. So therefore, the complex conjugate of z will be equal to b e to the minus I phi, and I want that to be equal to y, right, so that y and z are the complex conjugate of each other. And so what this now gives me is I'm free to choose this, so I'm choosing z to be equal to b e to the I phi, and then I'm choosing y to be equal to b e to the minus I phi. And that will then make my solution real. So I'm picking values for these complex constants to make my solution real. In other words, I'm giving up 2 degrees of freedom. I'm giving up the imaginary degrees of freedom in order to get rid of them. So what does this mean? Well, now when I write out my solution, what I have now is I have b, now e to the I phi times e to the I omega t, so that's e to the I omega t plus phi, and then I have here, I have plus b e, and then I have minus I, omega t plus phi here. And this is now my solution. So let's write this out longhand. So here this is b, and this is going to be cos omega t plus phi. And then I've got plus I times b sine omega t plus phi. And then I've got to add to this, I have b cosine omega t plus phi minus I times b sine omega t plus phi. So this term and this term cancel with each other, and what I'm left with is 2 times b cosine omega t plus phi. And so now, to finish things off right at the bottom here, I'm going to define a, which is equal to 2b. So a again is a real constant, just like b. And what that gives me now is a solution that looks like this. X as a function of t is equal to a cosine omega t plus phi, where phi and a are real constants, and omega is given by the spring constant, the square root of the spring constant divided by the mass. So this is my solution that I've now got to my oscillator. The question is, what do all of these numbers mean? And to do that, we have to plot this function as a function, this displacement as a function of time. So we've just derived the motion of a simple harmonic oscillator such as this mass spring system here. And now what we need to do is understand what all of these constants mean and how they relate to the amplitude of the motion and all the other parameters of the motion that we discussed at the start of this video. And we'll do that in the next video.